Today I'm pleased to introduce Gurtina Besla to give the CFA colloquium. So as some of you may know, Gurtina received her PhD from our department at Harvard in 2011. And shortly after that, she got a Hubble Fellowship that she took to Columbia. And after only a year as a Hubble Fellow, she was offered a faculty position at the University of Arizona, where she is now and where she has recently been promoted to tenure. So Gurtina is very well known for her work on dynamical modeling of the Magellanic Cloud system. So as a student at Harvard, she developed a new model for the evolution of the Magellanic Clouds based on proper motion measurements done by Charles Alcock and his collaborators, in which the clouds are coming into our galaxy for the first time. And so this is a new theory that's contrary to what was previously assumed, where people had imagined that the Magellanic Clouds were orbiting the Milky Way for many gigayears. And it turns out that Gurtina's model can explain many features of the Magellanic Cloud system that are quite hard to understand otherwise if they have been orbiting the galaxy for many gigayears. Her work has been very influential, and as a consequence, she's gotten a number of awards for her studies, starting with the Quito Prize from the CFA in 2011, the Trumpler Award given by the Astronomical Society of the Pacific for the best PhD thesis nationwide in the year of the award in 2013. More recently, the Bach Prize, again from our department, and the Vera Rubin Prize from the American Astronomical Society in 2017. In addition to her studies of the Magellanic Clouds, she has been very influential studying the dynamics of small groups of dwarf galaxies, similar to what we think the Magellanic Cloud system might have been before it fell into our galaxy. And today she's going to tell us about how the LMC system might be interacting with the Milky Way and implications of this for cold dark matter theory. Gurtina, please take it away.
Great, thank you very much. So what I'll be talking about today is this area of research that is known as Near Field Cosmology. And this is an area that aims to test our models of structure formation and dark matter using local probes. By local probes, I mean stars in the halo, stellar streams, satellite galaxies that are orbiting our Milky Way. This area of research has seen rapid growth given data from HST, Gaia, the H3 survey, Dark Energy survey, and in the near future, we'll have the LSST survey, DESI, WEAVE, Foremost. Basically, there's going to be this huge influx of data. And what I want to talk about today is the impact of the Milky Way's most massive satellite galaxy, the LMC, on our ability to connect these data sets with theoretical models and actually realize the true potential of 6D phase space information, so three-dimensional velocities, three-dimensional positions, to test cold dark matter theory. And I'm going to be arguing that the LMC is a challenge, but the challenges are surmountable, and there's going to be some brand new opportunities to test cold dark matter theory in completely novel ways. So the work that I'm going to be presenting is largely driven and led by my graduate student, Nico Garavito Camargo, and who's going to be giving the talk next week, the GCSP seminar on Friday, on October 19th. And also this is work that has been driven and led by Ekta Patel, a former graduate student and now Miller Fellow at UC Berkeley. In particular, this image that I'm showing here, we have sort of cold dark matter framework of filamentary structure and these nodes where galaxies and clusters grow. And then over here is sort of is an image from Nico's recent paper that was on the archive last week that shows the perturbations that are being induced into a spherical distribution of dark matter around a Milky Way owing to the LMC. And in particular, here is this sort of classical dark matter wake that may be generated in a dark matter model. And the notable point is that these structures and asymmetries may occur on much larger scales and in areas of the sky that the LMC hasn't even passed through. Okay, so the way that I would think about this talk is sort of part one, where I'm going to lay the sort of big picture groundwork, and a lot of the details, particularly of this model and of what this really means for our understanding of the dark matter distribution of the Milky Way, I'm leaving to Nico to talk about next week. Okay. So a little bit more detail with near field cosmology. The idea here is that we're trying to test cold dark matter theory with local objects. And this is a dark matter simulation, high resolution zoom in of a Milky Way type galaxy, or Milky Way type halo. This is the Via Lactea 2 simulation. So our Milky Way in this distribution would be right in the center, a very small object with respect to this larger distribution. So some of the things that we're trying to test locally, and this is not an exhaustive list, I just listed 3 things here, but one is the subhalo mass function. So you can notice that this distribution isn't smooth. There are a number of self-gravitating clumps that we call subhalos within the larger parent halo. And how many these are per mass bin is a prediction from the various different dark matter models that we have. Right, so there's a lot of effort that's trying to understand and hunt for dwarf galaxies, which are expected to populate each of these small blobs in this image, and try to understand how many they are compared to the distribution that we would expect from theoretical models. Another thing that we're interested in is the mass, the total mass of the galaxy or of the halo, and also its shape and its profile. So if you look at this distribution of dark matter, you'll notice it's not perfectly spherical. There's an elongation along some direction, and this may be telling us about the direction through which filaments, for example, have been built up and bringing in material into the primary halo. This again tells us something about the large scale structure of dark matter, which connect back to the various models that we have for structure formation. So understanding the shape is important. And ultimately, the structure that's around our Milky Way, some of it is coming, through smooth accretion in these filamentary structures, but there's also material that's coming in these individual clumps that are then disrupted. And the galaxies that reside within them will leave an imprint in this, what we call the stellar halo. This is this distribution of stars that surrounds our galaxy out to, of order 100 kpc or so. And these stars are distributed in streams. Some of it is smooth, some of it is clumpy. We have the remnants of these processes. Some of them are remnant satellite galaxies, globular clusters. And so this is what we actually see. And what our whole aim of cold dark matter, of near field cosmology is to take observations of this distribution of stars, both in terms of their positions, in terms of their kinematics, their chemistry, and then link them back to that, right? We want to go from one to the other. And this is, sort of the challenge that's being presented. And what the idea is that if you have perfect information, if you have the exact 3-dimensional velocity vectors, 3-dimensional positions, you may be able to reconstruct a stream, recover the assembly history of our galaxy, and ultimately recover the mass profile, right, of the Milky Way. So this is the goal. And it's super exciting right now because there's just so much data that's coming out. And frankly, the data that's come out of Gaia, I think, has beat everyone's expectations for what it was actually going to deliver. And it's making a lot of these promises from years ago actually realizable. And so this is a really exciting time to be doing this kind of work. So this is an image of our Milky Way. And when we're talking about these theoretical pictures, we have a few blobs here or there, right? But when we're talking about our Milky Way, it's not like it's got a number of small structures all over the place. It has those, but it also has 2 large structures. These are the Large and Small Magellanic Clouds that are readily observable in the southern night sky. Right, so this is an image zooming in on the largest of those 2 galaxies, the Large Magellanic Cloud. This is referred to as an irregular type galaxy, but it is a barred 1-armed spiral. And this structure, this offset bar and 1-armed spiral, has named an entire class of galaxies referred to as Magellanic Irregulars. And as Lars mentioned, I've done a lot of work in understanding the structure of the LMC and its interaction history with its companion, the SMC. So, but one of the things I want to stress here, and this is one of the reasons I'm so excited about working in local group astronomy and in the area of near field cosmology, is because I'm working with objects that are known to humans since there were humans on the Earth. Right, the LMC and SMC have been an important part of the night sky for many different civilizations in the southern hemisphere. Europeans discovered it when they came towards the south and actually traveled into the waters, for example, Ferdinand Magellan. But of course, they've been part of all the different civilizations in the southern hemisphere. Their history, their culture have surrounded the night sky, and the Magellanic Clouds play an important role in those stories. And so I find it exciting to work in an area where when I talk about an object, there is an importance and a profound understanding of these systems as a part of human civilization, right? So I think that's really cool. Just sharing a little bit about why I do the work that I do in this area of research. So what we've been trying to do in my team and through my work is try to understand more about where the Magellanic Clouds came from. So they've been a part of human night sky, but have they always been there? And you know, a lot of the new work that we can do now in understanding the history of these galaxies comes from new observations of their speeds. And this was work that was led by Nitya Kalivailil and Charles Alcock to actually clock the speed of the LMC. And then as a graduate student, what I did was took that work and applied it to a basic model of the Milky Way to try and understand the orbital histories. Now, since then, there's been a lot more work that's been done. In particular, Ekta has taken this picture of a Milky Way and an LMC and then added, you know, an SMC to try and understand the orbital history. And in addition, she's allowed for the Milky Way to respond to an LMC that's coming in. So in other words, it's not a fixed point in space, it also moves. If you think of a normal two-body problem and there are two objects, the center of mass isn't necessarily right where the Milky Way is. It's going to be a little bit off. And as a result, the two bodies move around some common center. So when you account for this and added these extra, you know, perturbations, we can revisit the story of what is the orbital history of the LMC. So focusing in on the center panel here, this assumes that the Milky Way has a total mass of around 10 to the 12 solar masses. And we know the position, this is the relative distance of the galaxy with respect to the Milky Way, and this is as a function of time. So we know the position and speed here, wasn't today. And we can adopt a model for the Milky Way and a model for the LMC, you know, account for things like dynamical friction and go backwards in time and actually look at the orbital history of these galaxies. And what we find, these are three different LMC mass models in these solid lines. And what you find is that the LMC hasn't been around the Milky Way for very long. And, you know, so most of these orbits are coming in for the first time within the past 6 billion years. You know, the mass of the Milky Way is uncertain, and I'll talk a little bit more about this later. So if you go to a higher mass model, it's possible to get a different orbital history. Again, starting from the same position and velocities that we know today and going backwards, you can even potentially get another orbit around the Milky Way. But this happens 5 billion years ago. And the other thing to note is that the bottom here, these dashed lines, are telling you about the orbit of the SMC around the LMC. So this is the distance of the SMC from the LMC as a function of time. And if you go to a higher mass Milky Way model, it is almost impossible to keep the LMC and SMC as a binary. This is a problem because we know that they have a shared history. There's a bridge of gas that connects the two of these galaxies. There's a stream of gas that trails behind them. They have correlated star formation histories. So these indicate that these systems have probably been around for around each other as a binary system for some period of time. But in a scenario where you have a more massive Milky Way, the orbits will always separate. And what this means is that the LMC would come in maybe 5 billion years ago, make one passage at 100 kpc radius, capture the SMC, and then continue its orbit, right? So that's the scenario. Or they came in as a binary on a first infall. And this particular scenario is more cosmologically probable, just in terms of statistics. You see this scenario happen. This is exceedingly rare. The Milky Way being in a higher mass model, and this case where the LMC randomly captures the SMC if it came in for the first time 5 billion years ago. So this is all to say that I'm going to move forward in this talk under the assumption that this scenario here, where the LMC is coming in for the first time with a bound SMC, is roughly the scenario that we're talking about, right? So I'm going to assume this is the assumption. And if anyone has any questions about this other scenario, we can talk more about it. What's interesting is that even in these cases, if you want to keep what the amazing observations that Nitya had spearheaded with HST, not only clocked the speed of the LMC, but it also clocked the speed of the SMC. And in particular, you can actually get a very accurate measurement of the relative speed between these two galaxies. And it turns out to be quite high, about 100 kilometers per second. So to keep the SMC in a binary around the LMC, you actually need the LMC to be fairly massive, on the order of 10 to the 11 solar masses, in fact. So this now brings in a second new piece to the story. So first of all, the LMC hasn't been around for very long, coming into our vicinity within the past 2 billion years, right? Virial radius is something like 250 to 300 kpc. So about 2 billion years ago or so, it's come into our vicinity. And in order for it to have come in with the SMC, it also needs to be fairly massive. This is actually completely consistent with cosmological expectations. If it's come in for the first time, we can actually use cosmological models to estimate the infall mass of the LMC. And what's shown on the right-hand side here is a plot from Ben Moster's work using a technique known as abundance matching. And so this basic idea is you have a galaxy survey with a large number of galaxies, and you can add those galaxies up in a histogram, binning them as a function of mass. So how many galaxies do you have in a given mass bin? And you can do the exact same thing with a cosmological simulation. You bin up your halos how many halos you have in a given mass bin. And effectively, you match the two. And so you can do this statistically. And this tells you then correlates the stellar mass of a galaxy to the expectations of what halo mass it should have had as an isolated system. So for an LMC, which has a stellar mass of around 3 by 10 to the 9 solar masses, this would put you in a halo mass of something like 10 to the 11. So in particular, the average result is about 2 by 10 to the 11. This makes it the encounter between the LMC and the Milky Way at least a 1 to 10 mass ratio encounter. And it could be as high as a 1 to 3 encounter. So we're in a very different scenario than we were prior to 2010. Earlier models of the Magellanic Clouds have essentially assumed that the LMC is fairly tightly truncated at this point, in which case its total halo mass is of order 10 to 10. So we're talking about a factor of 10 larger mass for the LMC than what has been traditionally assumed. I'm going to go back in time a little bit and talk about a paper by Elaine Abner and Ivan King. And so Elaine Abner, so Dr. Abner wrote this paper as her thesis from 1964. And in this paper, she explored the influence of the Magellanic Clouds on the Milky Way. And what's interesting at this period of time is that folks thought that the Milky Way was in fact of order 10 to the 11 solar masses. And so in this paper, what she posits is that the LMC is in fact on a 1 to 10 mass ratio encounter with the Milky Way. So this paper is amazing. It's, the assumption is the Milky Way is lower in mass, but the consequences for the mass ratio of the LMC and the Milky Way is very similar to what I'm saying right now. And in this paper, she argues that, contrary to widely held belief, the gravitational effect of the Magellanic Clouds on the Milky Way is indeed serious. And what she's talking about in this paper is that the LMC can in fact induce warps in the galactic disk with this 1 to 10 mass ratio encounter. And she does a wonderful calculation of this all. There were some errors in the analysis, which I think is why it was largely dismissed as the work continued onwards. And then this work was then examined in more detail by, for example, Alar Toumari did some fantastic work on the interaction of the Magellanic Clouds and the Milky Way. But I think it's just really interesting that we've come back to the scenario of a 1 to 10 mass encounter and revisiting the kinds of ideas that have come out in this paper. And in particular, there was another one, which was really thinking about the binarity of the Magellanic Clouds, that these two galaxies, if they are actually bound to one another, they could not have been around the Milky Way for very long. And in this paper, they explicitly say that the clouds are probably bound to each other, but they're passing by our galaxy in a hyperbolic orbit for the first time. And in particular, the argument is made that the LMC needs to be quite massive in order to hold on to the SMC. So I'm talking about this work because I think it's been sort of lost in the literature, and I think it's a really phenomenal paper that deserves attention. And I think it's also as a note to students who are in the audience that most of the topics that we're talking about have a very long history, and it can be a challenge to go through and find all of these works. And we can find works that have been dismissed for various reasons, but it's always important to revisit those stories and those ideas from before to see if they have merit with new data and a new perspective. So there's a lot of evidence that the Magellanic Clouds have been coming in for the first time. I've talked a little bit more about the LMC and SMC binarity, but I think another important one that's been realized with new data sets is just the size of the LMC. And so the spatial extent of the stars associated with this galaxy, the images that I've shown you up to now have really been focusing in this region here. And it's about 10 degrees less than, actually, it's about 8 degrees on the sky. And at the distance of the clouds, this corresponds to something like 1 degree is about a kiloparsec. So with recent work from using data from the Dark Energy Survey, this is work that's been led by Dougal Mackey, has shown that there are stars associated with the LMC out to as much as 18 degrees away. So the total diameter of the stars associated with just the LMC is something like 35 degrees, which would make the diameter of the LMC's disk 35 kiloparsecs. And it's only 50 kiloparsecs away. So the idea that the disk hasn't been truncated to anything smaller, given its current separation of 50 kpc, is, in my opinion, very strong evidence that the clouds haven't been around the Milky Way for very, very long. So we have a massive LMC coming in within the past 2 billion years. It's about a 1 to 10 mass ratio at worst, right, or at best, but it could be as high as 1 to 3. And so now we want to understand what the implications of this. What are the challenges presented? What are the opportunities that this presents for our usage of these new astrometric data sets that are going to come out? What are we going to learn about cold dark matter theory and about the evolution of our Milky Way in light of this massive perturber? So this is work that's really been spearheaded by Nico Garavito Camargo. And so I'm going to show you sort of a simple rendering of what's going on. So let's assume that the Milky Way is a spherical dark matter halo prior to the infall of the LMC. This image is showing you density contours. So isodensity contours are all spherically concentric rings, essentially, right? And there's no LMC. So this is about 1 billion years ago. The LMC is only just entering the Milky Way's vicinity. And then about 50 million years ago, it makes its closest approach to the LMC. And you'll notice that these isodensity contours that were once spherical are no longer. They're more elongated in the direction of the LMC. And then if you go to present day, which is another 50 million years, once again, these structures are no longer spherical, but they're also very different than what they were 50 million years ago. And what's relevant about this is that the time scale of these perturbations are comparable to the dynamical time of everything orbiting in the halo. Right? We're talking about a gig-a-year timeline of perturbations. So, so where do we go from there? So this image here is showing you, this is the Milky Way plus all of the LMC dark matter distribution and any perturbations that's induced. It's sort of everything all on top of one another. And the work that Nico's been doing has been to decompose this using basis function expansions and actually understand what is the component of the perturbation that is owing to the LMC particles versus the Milky Way. How do you compare the Milky Way structure from what it was originally to what it is now? And so I'll just show this image, and I'm not going to bring it up in detail anymore because Nico's going to explain it in much more detail later. But this is what the distribution would look like, the residuals effectively, if you took out all of the LMC particles and you took out the dominant spherical terms in the expansion, the monopole term, and this is what you're left with. And so there's a highly asymmetric structure. It's extended on the sky. This is, almost the size of the entire virial radius of the Milky Way. And in particular, there is this transient structure here, which we refer to as the dark matter wake. So what we want to know then is, how big of a problem is this, right? What does this mean? Are there new opportunities that are being presented, right? So the argument that I'm going to make is that this infall of a massive LMC is presenting both challenges and opportunities for the test of cold dark matter theory. Okay, so I'm going to sort of list through a few different things. It's going to be a lot of things, but I'm excited about a lot of things, so I figured I would share as much as I can. And so the first one is an opportunity. And then we have an opportunity to constrain the subhalo mass function at low masses. So what do I mean by this? In different dark matter models, we have different predictions for the subhalo mass function at the low mass end. And so this is images taken from Mark Vogelsberger's work, where he has looked at the substructure problem in a cold dark matter model, and then with modifications to what you assume are the properties of dark matter. And as you change the properties, you can actually remove substructure at the lowest masses. And so what we've primarily been doing as a field has been trying to explore, how many of these substructures actually correspond to a satellite galaxy, like a real system, using very deep observations and trying to detect satellites around our Milky Way. This really is the main place where we can explore the very lowest mass end of this mass function and trying to find the lowest mass galaxies that exist. Right? You can only really do this around the Milky Way and hopefully in the near future around M31. So, the idea again is if we can really probe to lower and lower mass scales, we can start to constrain the properties of the dark matter particle. But we've primarily been thinking about this in terms of the satellites of the Milky Way, right? Or the satellites of Andromeda. And what we now have the opportunity to do is to think about the satellites of the LMC, right? So we can start to understand how many systems should have come in with the LMC based on cold dark matter theory, and how many do we actually see. And the reason that we can actually determine which ones are in fact satellites of the LMC is because we now have 60 phase space information, so three-dimensional velocity vectors and positions for satellites, and this is largely thanks to Gaia. So, one of the key things has been discovering satellites. And as I mentioned, we've known about the Large and Small Magellanic Cloud since there were humans. And then, in the 1950s, we start to find some of the other lower mass satellite galaxies that are orbiting around our Milky Way. And then eventually we get the Sloan Digital Sky Survey, which opens up all this discovery space in the north. And then the Dark Energy Survey comes online, and we get all of these points in green are showing up here as the new satellites that have been discovered in the Southern Hemisphere. So this image was compiled and movie was created by Marcel Pawlowski. So where we're at today, this is I think probably the most up-to-date compilation of all the satellite galaxies that we know about around our Milky Way by Alan McConaughey in this very nice review paper. And so there's a large number of them, but you can notice that there is a clustering in the south, right? And this is around the LMC in particular. And so what I'm arguing here is that this is an opportunity, now that we've discovered all of these systems, and there are Gaia now proper motions for a large number of these systems, and some of them are also coming from the Hubble Space Telescope. Combining this all together, can we actually pull together a gravitationally bound group around the LMC? So this is work that's been led by Ekta Patel, and what she did is created models of the orbital history of satellite galaxies that have the highest probability of being associated with the Magellanic Clouds. So these are all panels that are showing you the distance on the y-axis between the satellite and the Milky Way. And on the x-axis is the time, where 0 is today. So this is the distance as a function of time. And you'll notice there's a whole variety of different types of orbits that can come out for all these different satellites. And the orange line and the blue lines are just telling you two different Milky Way mass models. So, as I mentioned, the mass of the Milky Way is uncertain. So the lower mass model, 10 to the 12, is in blue, and in orange is the higher mass Milky Way model. In these calculations, Ekta included perturbations from the LMC and from the SMC. So to think about this binary system having a group of satellites with it. So which of these systems could potentially be actually satellites of the LMC? Now, the error bars on some of these proper motions are still very high. So this is all preliminary estimates using the mean velocity vectors that we get out from Gaia. And what we find, so what Ekta found is that there are a number of satellite galaxies that look like they're orbiting around the LMC just from these plots. So what you'll notice is that their orbits, and if you look at Phoenix 2 is a good example of this. Not sure where my cursor went, but anyway, Phoenix 2 shows sort of wiggles, right? There's a larger orbit around the Milky Way, a larger period, and then there's another frequency on top. And so this is indicating that Phoenix 2 is in fact orbiting around another body as it's orbiting around the Milky Way. So what you can do then is compute the orbits of all of these satellites, and you can ask, what is the speed of these satellites at the closest approach that they had to the LMC? And you can compare that to, for example, the escape speed. So we have a number of these satellite galaxies that are potentially associated with the LMC. Then we ask in this orbit calculation, how close did they ever get? And there's a clustering around the x-axis is the distance between the satellite and the LMC, and the y-axis is the speed at that closest approach. And what you find is that there are a number of these satellite galaxies that make a close approach within the tidal radius of the LMC, and that have speeds that are less than the escape speed associated with that distance. And so what you find is there is, in fact, a number of satellite galaxies that aren't associated with the Magellanic Clouds. These are in black. And then there are a few that have recently interacted with the LMC. These are the ones at high velocity, but at close separation. Yes, like Tuck-3 is an example. And then there are a few others that are likely to be satellites of the LMC. So CAR2, CAR3, Horologium 1, Hydra 1, Phoenix 2, Reticulum 2 are possibly recently captured systems. And so essentially what we find is that there's about 3 to 5 satellites then add in the SMC, so 4 to 6, within the Milky Way's halo that have actually show kinematics to be consistent with being an accreted group associated with the LMC. And this is consistent with cosmological expectations, where you would get something like 5 satellites for an LMC type host, where the host is 10 to the 11 solar masses, right? So the assumption here is that the clouds have come in for the first time and they are massive bodies. Under that assumption, cold dark matter would predict about 5 satellites. And in fact, that is roughly the number that you find. So everything seems to be lining up quite nicely. To highlight that there's also predictions for satellites of the LMC have been done by a large number of authors. I've listed a number of them at the bottom of the slide. So this is a movie that EICTA created to sort of illustrate this Magellanic group infall, where you have an LMC and an SMC on your right-hand screen and the satellites in purple orbits around them. And you can see the systems are orbiting around the LMC, including the SMC going around the LMC as they come in to the Milky Way vicinity for the first time within the past 2 billion years. What's exciting about this is that it also means that there are, we've thought about the LMC and its satellites, but there's another massive body that actually has similar mass to the LMC, and it's called M33. This is a satellite of Andromeda. It's also likely on its first infall towards the Andromeda environment. And it should, at the same time, also have satellite galaxies. And M33, one would expect to have about 8 or so satellites with stellar masses greater than 10 to the 4. And these were predictions made by Ekta Patel using models from by Dewey et al. And the Caterpillar simulations. And what's exciting is that there are going to be new observational surveys around M33 to look for this. And so this new data coming out to try and actually assess whether or not M33 has satellites, as one would expect, and therefore is its subhalo mass function consistent with cosmological expectations. So that's the first one. I think that this is new territory. We have this opportunity of searching and understanding this, environment around an LMC mass host. And now this, with 60 phase space information, we've identified those satellites that likely came in with the LMC. Okay, so another one I think is an opportunity, and I think this is just new parameter space entirely. So all dark matter models predict that satellite orbits will decay owing to dynamical friction. And this decay will happen to some degree. And by saying to some degree, because some of the dark matter models predict higher or lower levels of dark matter, of dynamical friction. And so to illustrate the point, so on the left-hand side, this is an image that I've shown you already. The LMC comes in, it orbits within the dark matter halo of the Milky Way. And what's shown on the right is a movie illustrating the overdensity that is generated behind the LMC as it's orbiting through the dark matter halo of the Milky Way. So the LMC center is designated by that black dot, but it is an extended body in the simulation. We're just not showing the LMC particles. And the structure that you see behind it in red is the overdensity associated with the creation of a wake. So in dynamical friction, the idea here is that as a perturber is moving through some ambient medium, it actually generates a gravitational force on that medium. And since it's moving, it's actually pulling all of these particles towards it and generating a wake behind it as it continues to move. This process is in fact a resonant process. So it's not just a local gravitational force that's acting on bodies. It can be augmented based on the orbit of the satellite itself. And as a result, these structures may not occur just behind the LMC. You may get structures at larger distances. And if I pause the movie right towards the end, you'll notice that the wake strength evolves, right? It decreases. And there's other structures that happen in the north. And so the perturbations that we're seeing here are not just this classical wake structure that would expect it from Chandrasekhar's models, but in fact, you'd get resonances that can augment this structure at larger scales. If you're curious more to read more about this, I would encourage you to look at Martin Weinberg's work on this topic. So, but the clear point here is that in a cold dark matter theory, we have the codes to actually generate the exact prediction of the wake structure that you would expect to trail behind the LMC. So the opportunity that we have is to look for it, right? We're having the 60 phase space information for the stellar halo. And if we assume that there is a stellar halo that is in equilibrium with a dark matter halo, then the wake that is generated in the dark matter distribution is expected to also be seen in the stellar distribution. and they should be of comparable magnitude. So we can use these simulations, and this is work that Nico did in 2019, to make predictions for what we may observe in upcoming surveys and current surveys, including H3, Gaia, LSST, et cetera. So this movie that I'm showing you is walking out in distance slices of the present day expectation for the dark matter halo of the Milky Way and correspondingly the stellar halo. And the color scale is showing you the overdensity of these perturbations relative to the ambient background. So 0 would be basically no perturbations whatsoever, and the value of 1 would be a factor of 2, essentially increase in the density. So the very red is a factor of 2 increase. The stars are telling you where the LMC was as a function of time. Going towards the right, this is backwards, and towards the left here, this is the future orbit. And what's interesting is that you're finding perturbations in the north, which is a region of the sky that in this model, the LMC never even traveled through. So you'll have a very clear pattern of what we would expect in a cold dark matter model for the distribution, for the structure of the wake on the sky. And we're hoping that this could potentially be observable. So it's not just a density perturbation, there are also stars, the particles are actually moving around. Mass is conserved, so if the density increases in some region, it must have come from somewhere. And so you're getting material that is flowing into this wake structure. And so we've also been working on making models for the expected kinematic signature that may be observable in if you had 60 phase space information. So what I'm showing you right now is v theta, v phi. So these are the tangential motion or tangential velocity field. And I'll talk about the radial velocities in a bit. So on the left is sort of a prediction. This is the predictions from Nico's paper of the structure of the wake on the sky, including the structures in the north. And then on the right-hand side in the top panels is the corresponding velocity field that you get from the simulations. And then phenomenal work led by Emily Cunningham, who is a postdoc at the Flatiron Institution, has looked at this velocity field and then applied a harmonic expansion, spherical harmonic expansion, to try and understand how we could tease out the signal from a data set that only gave us, for example, v theta, v phi. And so what she showed is that actually a fairly low order expansion, like order of 5, L max equals 5, can actually effectually capture the salient features that we would expect in the velocity maps. So what these features actually are is when you look at the wake, the structure of the wake, you're going to get stars that are going to converge towards that wake structure. But dark matter in this model is collisionless. And so what happens is the dark matter particles essentially flow past one another. And so you'll get diverging flows in particular v phi. So the bottom right panel shows this bright yellow region is actually moving towards the left and the dark blue region is moving to the right. And so you expect to see diverging flows in these models. So this is this may be more pie in the sky to try and actually observe this kind of structure, but it does sort of mean that you would actually have very particular kinematic signatures associated with this structure. So if you can observe the signatures that are consistent in terms of kinematics and density, we may be able to put that together to have a smoking gun for discovering this structure. The key point of it being a dark matter effect is that the amplitude of this wake would be much lower if there wasn't dark matter there, right? You would get a dynamical friction wake even if you just had stars there and no dark matter. But you need a very massive LMC to generate the wake of this type of magnitude. So that's the important point about it being a cold dark matter or dark matter test in particular. We've assumed here that the structure of the halo is smooth. Of course, it's not. We believe that the halo has been built up through the accretion of multiple events. And to date, what we've mainly focused on is the impact of the Sagittarius dwarf on our assumptions. And in terms of the velocity field, Emily has shown that the Sagittarius's perturbations are minimal in comparison to what the LMC is doing at these types of distances. So just for reference, the Sagittarius dwarf is creating a stellar stream, is being tidally disrupted and has a tidal stream across the sky. On the bottom left, I'm showing a model and the X's are showing data points for the Sagittarius stream stars that are strewn around our Milky Way galaxy. And this is a model from that was created by Marian Diericks. And the right-hand side here is now showing results of including Sagittarius in our estimates for what this wake would look like on the sky. So the left-hand side is the perturbations from Sag. The middle column is the Sagittarius plus the LMC, and on the right-hand side is subtracting out Sag's impact. And in the end, what you're left with is just, it really is the LMC is what you're seeing. And the main reason for this is because the Sagittarius dwarf has been around the Milky Way for a long time. It's made multiple orbits. And as I showed you in that movie, the strength of the wake actually dissipates over time. And as we have repeated orbits, you're going to have more of the dilution of this effect and in the halo. Furthermore, the Sagittarius dwarf is in fact on an orbit almost exactly perpendicular to that of the LMC. And as a result, its perturbations are actually happening in a completely different area of the sky. So we do believe that it should be hopeful to observe the structure in the night sky. So continuing on in this theme of opportunities and challenges, astronomers are currently trying to use the motions of stars and galaxies orbiting around the Milky Way to constrain the distribution and the total amount of dark matter that exists around our galaxy. But as I've mentioned, we have an LMC here, and the LMC is about 50 kpc away. It's like a 1 to 10 encounter at, again, it could be even higher. And as a result, the orbital barycenter of the LMC Milky Way system is not where you think it would be. Basically, traditional models assume that the center of mass of the Milky Way and its satellite system is the center of the Milky Way's disk. But if you have a massive perturber in the south, that orbital barycenter is in fact offset by something like 15 kpc. And as a result, the Milky Way's center of mass is going to shift. It'll move. And that motion can be as much as 10 to 20 kiloparsecs and speeds of 40 to 80 kilometers per second. Right. So this is a movie kind of illustrating this. So there's the LMC coming in for the first time. And what I'll try and do is play this again, is this is the original center of mass of the LMC where my cursor is. And you'll notice that the Milky Way center moves. But it's not the whole body moving as a solid structure. It's actually just the inner cusp that moves. And the outer outskirts of the halo is in fact lags, it stays behind. And what this means is that for us as observers in the center of this galaxy that's moving, we're going to observe the reflex of this motion imprinted on the sky. But that reflex motion will change as a function of radius because some portion of our halo isn't moving. And it's just the inner regions inside that are actually moving. So this is a simulation, once again, walking out in radial bins to try and look at what this reflex motion might actually appear on the sky as an observer in the Milky Way's disk. And I'll just stop it here. This is an example at 75 kpc in all sky image. And the black regions here are showing you material that is moving towards us. And then up here, these lighter colors are showing material that's moving away from us. And so effectively, we expect there to be a large scale dipole on the sky owing to this effect. What is going to be problematic about this? Well, first of all, I'll say an opportunity. The magnitude of this dipole should be telling us something about the density of the cusp. How much is the inner regions of the Milky Way able to move with respect to this LMC that's coming in will depend on the mass profile. So there is information here, if we can observe this, that could potentially be teased out to tell us something fundamental about the mass profile of the Milky Way, or even in fact the mass ratio of the Milky Way and the LMC. But there is also a problem, or at least a challenge. Standard models that we use at the moment to determine the mass profile of the Milky Way assume equilibrium. These are typically gene modeling techniques. And what we do is we take some body of stars or globular clusters, and we apply genes modeling to then use the kinematics of those objects to infer the underlying potential. And that gives us a constraint on the mass profile. But I've just told you that there's this sort of global shift, particularly at larger radii, that's happening. And what's interesting is that the current mass profile of the Milky Way is uncertain within a factor of 2. This is a plot from Gwen Eadie's work. And there's estimates that are taken in the inner regions that are then extrapolated out to large distances to get estimates at large scales. And there's also the LMC sitting in the middle here. So what's happening is that the tracers in the inner regions may be telling us a very different story than what the tracers in the outskirts are actually telling us about the mass profile of the Milky Way. A factor of 2 in certainty in the mass of the Milky Way, as a theorist, is pretty good. Like, it's really not that bad. But when we're talking about trying to do precision cosmology, that is a huge problem, because a factor of 2 is enough to still say there could be a missing satellites problem, or a missing baryon problem, where we're trying to find all of the baryons that you would expect from the cosmic baryon fraction of about 16%. They have to be hidden in the halo. And if the mass of the Milky Way could be 2 by 10 to the 12 solar masses, that's a lot of gas to hide away in the halo someplace. So a factor of 2 is a problem. And the argument is that the LMC is in fact going to cause an extra difficulty in actually coming up with what this number really is for the mass of the Milky Way. And so, you know, I present this as a problem or a challenge, but it sort of depends on what question you're trying to ask. I think if we want to know the mass of the Milky Way today, I think there's actually a lot of ways to come up with this, particularly the mass tracers in the outskirts are going to tell us the combined mass of the Milky Way and the LMC, which is the total dynamical mass of the halo. But if you are trying to recover the mass of the Milky Way before the LMC came in, and that's the mass that's actually interesting to compare the Milky Way against cosmological models, right? If you want to know, is the Milky Way in fact a typical halo? Does it actually agree with cosmological expectations for the number of satellites it holds? All those types of questions. You need to take out the mass of the LMC. And that's trickier because, as I said, the LMC's perturbations are not, they're not just like a simple structure. It's perturbing the inner region in a different way than it's perturbing the outskirts. So there's a nice paper by Dennis Urkel to try and get a handle on this. And what he's showing on the right-hand side is, so the right-hand side top panel is illustrating the mass of the Milky Way in 3 different simulations where the LMC is included. So these are these triangles or squares or symbols. The dashed black line is showing you the mass of the Milky Way before the LMC came in. So as you get to about 50 to 80 to 100 kpc, especially for a more massive LMC, the actual mass profile is different than if the LMC wasn't there, as you would expect, right? So the bottom panel is just showing you the ratio between the symbols and the dashed line. So it's just the mass as a function of radius. On the left-hand side, Dennis has tried to recover the mass profile that you see from the simulations, which is shown on the right, using Jeans modeling. And essentially what he's trying to recover is the initial mass profile of the Milky Way. So what's shown on the y-axis of that left-hand panel is the ratio of what you actually get out from the Jeans modeling method versus the true or the pre-LMC infall mass. And so as a function of radius, you would overestimate the mass of the Milky Way before the LMC came in. You know, and you'll do this for, if you use all data from across the entire sky, that's these black symbols, which just returns you basically the mass ratio between the Milky Way and the LMC. But if you look at different regions of the sky, you actually get different answers. And that's what's troubling. The different regions the reason you're getting different results in different regions of the sky is because of the way the LMC is perturbing the kinematics of the halo. Essentially, this method of Jeans modeling relies on understanding the velocity dispersion in various regions of the sky. And in particular, as for most cases at the moment, we're reliant on just one component of the velocity vector, the radial velocity. And these maps on the right-hand side are showing you how the radial velocity dispersion can change across the sky. So depending on where you're looking at, you may be getting a very different set of kinematics because the system is not in equilibrium. So there is a challenge here. I think there is a way around it. Dennis has explored one avenue of doing it, and our team is building some more directions for how to think about this problem. But this is an issue. And again, this is just the beta profile as a function of distance, exploring the same type of point. The beta profile is changing, or the anisotropy of the halo is changing as a function of radius and also as a change of location on the sky. That's the problem. Okay, so I'm going to briefly talk about both the opportunity and challenge. And this is the idea of reconstructing the assembly history of our Milky Way. Now, the promise of 6D phase space information is that we can rewind the clock, recover orbits of satellites, streams, and globular clusters, and reconstruct the assembly history of our Milky Way. The problem, or the challenge, is that the LMC is there. And so what we're showing here is the orbit of a particle in the simulation, including the LMC or not including the LMC. And by what I mean by including the LMC, I also mean all the perturbations that's inducing, the wake, you know, the shift of the inner halo, all of that results in 2 very different trajectories between 2 particles in this simulation. So if you're trying to recover orbits and you're not including the perturbations from the LMC, this can be a huge problem. But there are a lot of parameters out there, like what is the mass of the LMC? What's your initial conditions for the Milky Way? So, you know, we need a large theoretical effort right now to try and develop these models in many different cases, including in a fully cosmological situation, to try and understand the degree to which you would get perturbations for the orbits of various objects, depending on, you know, what radius they are, what region of the sky they're in. And I think there's been huge strides. There's been a recent paper by Eugene Vasilyev to try and model the Sagittarius stream in a time evolving model that includes the LMC's perturbations. So basically it's a model like this that also has Sagittarius orbiting within it. And what they're trying to do then is recover, the simulations are in these small the colored dots, and then the data points are these squares. So they're trying to reproduce the stream that is observed using the simulation data, and that can actually help us constrain all the different parameters that we could potentially use. And they've actually generated a very successful model for matching this all that relies on the perturbations of the LMC. There's been a large body of work of trying to understand what the LMC is doing with the Sagittarius, with the Milky Way, and also how Sagittarius is impacting the halo of the Milky Way. And so I'd encourage you to look at these other authors on the left-hand side and the work that they've done. But this really does seem like the direction we have to move in. I still think there's a lot of work to do, but this is I think a really great step forward. The challenge that is going to remain though is how do we then take results like this and then infer something fundamental about the structure of the Milky Way's halo? Like, what does this actually mean about the structure and shape of the Milky Way? What is the LMC and Sagittarius and all these structures actually doing to distort our halo? And how do we then compare this against cosmological expectations? And so I'm not going to answer that question, and I'm going to leave that to Nico to address. I think one other thing I want to mention is that it's not just the Sagittarius stream that's being impacted by the LMC. There's a lot of other streams that seem to be showing these same kind of perturbations. There's work from Nora Shipp and Dennis Urkel's team, with the Orphan stream in particular. In order to explain the kinematics that we're seeing in these streams, it really does look like you need an LMC to perturb things, but not, you know, a 10 to the 10 solar mass halo LMC, something of the order of 10 to the 11. So we really are in this scenario where we have a 1 to 10 mass ratio encounter with the Milky Way. So as I mentioned, see Nico's talk because he's going to basically take things up from here. All right, I'm gonna just briefly mention this, and then I'm gonna stop and take questions. So the last opportunity that I really want to talk about was an opportunity for partnership with particle physicists that has been sort of brought up by this scenario, and that is that with an LMC that's moving into the Milky Way's dark matter halo, it's bringing within it its own dark matter particles, and it is possible that it's distorting the dark matter distribution in the solar neighborhood. So in direct detection experiments that are on the Earth, in order to actually understand the event rates that they're seeing in their detectors, you need to know something about the expectations of the dark matter distribution in the solar neighborhood, including the density profile, but also including the velocity distribution. Essentially what you're trying to detect in a detector is a dark matter particle hitting your detector, and there's a recoil, and that recoil will depend on the momentum that's transferred. That momentum depends on the velocity of the particle hitting it, but also the mass of that particle. So the idea is if you know the velocity distribution, you can also determine the mass of the particle that you're actually sensitive to in your detectors. So a lot of folks have been trying to understand what is the actual dark matter distribution of the Milky Way. And this is the input that astronomers give to particle physicists so that they can understand their results. The new picture that Nico has been really showing is that the LMC is coming into the Milky Way's halo, and that the LMC itself is an extended body, 10 to the 11 solar mass halo, but that structure is going to get distorted by tides. So you'll have some particles that are bound to the LMC, which are shown on the left, but there are also particles that are no longer bound to the LMC, and those are shown on the right. And in fact, a large number of these particles, or a reasonable number of these particles, are actually coming through the solar neighborhood of the Milky Way. So the dark matter debris from the LMC is expected to be the most massive debris of dark matter particles, or flow of dark matter particles, experienced by the Milky Way over the past 2 billion years. And it turns out that the impact of this on the dark matter distribution of the Milky Way is targeted at very high speeds. The LMC debris contributes something like 0.2% of the actual density. So it's not a lot of mass that it's contributing, but what's interesting is it's all at very high speeds. So in galactocentric velocities, this is at 600 kilometers per second. These are these blue histograms that I mentioned, that I show here. But if you account for moving to the Earth frame, you need to account for our motion around the galaxy, the sun's motion, and that boosts the signal to be something closer to 800, 900 kilometers per second. That's on the right-hand side. There's been a lot of work in the literature from the Gaia survey that's been finding a lot of substructure in the halo that it's at various different speeds. And there's been a lot of discussions about how this impacts the density distribution of dark matter in the solar neighborhood. And what's interesting is that all of these things that have been coming out of Gaia, these dark shards, as they've been called, are all less than 600 kilometers per second. Whereas what I'm talking about with the LMC is more at 800, 900 kilometers per second. Ultimately, what this means is that experiments today are actually more sensitive to lower mass dark matter particles or WIMP masses than they have been originally thinking about. Because typically the assumption is that you stop, that there's no particles that are moving faster than 600 kilometers or 700 kilometers per second in the Earth frame. So I think this is a new opportunity for conversations with particle physicists, which I'm excited about. So yeah, I'm gonna just stop here and I'll just sort of list these opportunities. I'm just gonna put them up here so you can look at them and I'll just take questions. Great, so thank you.
Thank you for the excellent talk, Gurtina. So we have time for some questions if anyone has them. So Marion has a question.
Yeah, thanks, Lars, and thank you, Gurtina, for a great talk. My question had to do with the slides you showed on Ekta's work fairly early in the talk, which showed different orbits of the LMC looking back in time. And you mentioned that she runs these simulations backwards, reversing dynamical friction. And I'm just wondering how that works, how things that are not easily reversed, like tidal stripping, for example, how that is taken into account in the...
That's a really good question. And I think the straight up answer is they're not. So these are the sort of starting points. And what we're finding is that so based on in a first infall scenario, the center of mass motion follows this orbit fairly well. And we know this because we've compared Nico's orbits to the analytic calculations that are here. So that's fairly reasonable. What's probably more suspect is the SMC's orbits around the LMC. You have some model for dynamical friction, but that absolutely doesn't account for the tidal mass loss or the distortions of the halo that are in there. I think that so I would say that for the LMC, the orbit is fairly robust, what's shown here in the 10 to the 12 solar mass halo model. Now for the 1.5 by 10 to the 12 solar mass halo model, that may be a little bit more suspect as well, because if there's a previous encounter at 6 gig years ago, you're right that the mass loss there would start to matter. And so we'd have to test that with a bit more detail to make sure that we're actually following, that this orbit is still realistic there. But I think that for the 10 to 12 solar mass model, it's fairly robust based on our comparisons with Nico's models.
Okay.
Sorry, Marion, did you have some more questions?
Oh, I just wanted to say thank you. And also, I guess I was excited to see the work of the student who was focusing on dynamic friction and whether those simulations might yield some insight on whether there's better approximations that we can use.
Yeah.
And because I don't know, it seems like the biggest obstacle to perfecting these sort of semi-analytic approximations of these orbits.
Yep. Yeah, no, I agree, because especially you have multiple orbits, like something like SAG, reproducing that orbit realistically in an analytic way is very difficult when you've got resonances that are operating over multiple timescales. But I think that's a really exciting area of research.
Thank you.
Okay, next, Warren Brown has a question.
Hey, great talk. It's clear that this time variable potential you're describing must be correct. So is there some tool that you or your group are developing that others could use, like to integrate orbits through this more complicated potential?
Yes, this is exactly the idea. And Nico's going to talk way more about this next week. So this is the main product that he's going to create. The plan is to make it publicly available within Gala, the Python package. And so that everyone can integrate orbits in this sort of model. And the nice thing with the way that Nico set this up is that he has created these basis function expansions that describe the LMC distortions. It describes the material that is bound and not bound to the LMC separately. It includes the Milky Way's distortions. And so you can actually isolate what is the wake doing relative to what is the direct torques from the LMC doing, for example. So I think it's going to be really powerful. And so the plans are hopefully by the end of this year, but pandemic, we'll see how things go, but to make that publicly available. So we'll make sure to keep you in mind, because I know you've been doing some great work with thinking about hypervelocity stars and the LMC's impact on that. So I think that's all really important and would benefit from this.
I think Anna Bonazza has a question.
Yes, thanks, Lars, and thanks, Gurtina. So my question is about those global responses that both Nico and Emily have been showing in the stellar halo of the Milky Way. And so, as you mentioned, there is a lot of substructure in the Milky Way from the accreted stuff. So I just wanted to kind of ask along those lines, how does this come into it when the original, like the unperturbed model of the Milky Way is not smooth, but actually has substructure in its own? Will we be able to untangle this?
Yeah, that's a really, really good question. And I think this motivates the direction we've got to go in. And we need to build models that have stellar halos that are more realistic to actually test this. So Sarah Loebman has done some fantastic work with looking at what the impact of substructure would be on the beta parameters. So various, like, you get these random dips and changes in the anisotropy profile of the halo because of substructure. So already that's going to complicate estimates of the mass profile using standard genes modeling type techniques, and it can be very depending on what region of the sky you're looking at. So Emily has done some work with quantifying the degree of perturbations you would get from substructure, and basically she found that if you're in a major merger type scenario, you're in trouble. So in that scenario, you're definitely going to have some big perturbations. For something closer to a Milky Way's accretion history, if you can understand how to handle SAG, I think there is a lot of hope for getting some of these smaller structures, like the responses that are shown on the bottom right of these pictures. I have more hope in terms of the radial velocity signal. Where was that? Yeah, this. So this sort of perturbation on the left-hand side, I think because it's so large on the sky, it should be something systematic. So I think that averaging over large areas of the sky and looking at the north versus the south, I think that you might be able, that it could be teased out. And in terms of the wake itself, the scale of it is so large that it, again, assuming that there is something there that is somewhat like super clumped, there could, you could also pull out that signal too, because it is so large on the sky. So I'm hoping that these sort of substructure effects are narrower or sharper in this space, that these global responses could still be discerned. The key is comparing areas of the sky. I think that's the key.
Awesome. Thank you so much.
I might ask a question, Gurtina. So the sort of studies that you've done, can you learn anything about the large scale structure around our galaxy from them?
I'm going to totally deflect that question to Nico. So you're going to have to ask him that next week, because this is exactly, I think, the heart of the problem. And that's, I think, what we have to figure out. It's not just the large scale structure. It's also, what was the shape of the Milky Way's halo before the LMC came in, and how are we going to figure that out? And if we can't do that, then like I said, the direction of near field cosmology is going to be focusing in on the wake and trying to understand, or SAG, or some of these other structures. But it's understanding the triaxiality of the halo is going to be a challenge. So I'm going to let Nico talk about how bad of a problem that is and what the prospects are for disentangling these effects.